Here we're looking at the energy interaction model, and this is what we're going to actually use as our technical definition for energy. So bear with me as we go through these statements, and we'll talk about it a bit in class as well. So first off, when we're talking about a model, we need to define the pieces that we're going to have interact with each other. So I'm going to list off a bunch of things here. You don't really need to understand in depth what each of them are doing, but just know that these are all the different places that energy kind of can exist. If we use an example of money, these are like kind of different bank accounts, so to speak, that energy can move between. So first, there's two types of internal energy that we're going to look at, and these are thermal energy systems. So thermal energy and bond energy. You don't need to really know these because we're not going to talk about them much in this unit, but thermal energy is basically the energy associated with how hot something is, and bond energy is associated with the chemical energy, right? So if you burn something, it releases energy. That's because of the bond energy. Next, we've got gravitational potential energy. This is the energy associated with how close or far an object is from the Earth. We've also got elastic or spring potential energy. This is the energy associated with how stretched or compressed a stretchy object is. We've also got electric potential energy. This is the energy associated if you've got two objects with electric charge, how close or far they are. And then lastly, we've got kinetic energy. So again, you don't need to know all of these for this introduction here. Just understand that these are different buckets or different bank accounts that energy can move between. Now we're going to talk about how these buckets relate to one another, or how we really define these buckets. So our first statement in the energy interaction model is that every physical change involves a change in, it shouldn't be a change in matter, it should be a change in an energy system. So anytime matter changes or rearranges itself or moves from one place to another, stretches, compresses, burns, explodes, all that stuff. Any physical change involves a change in energy systems or an energy system. A change in an energy system can be calculated by measuring a change in how do I have this phrased? A measurable property. We call this an indicator. And then multiplying by a specific constant. The indicator is the physical change we talked about in statement 1. And the constant is specific to that energy system. So I'm going to give you one example. I'll talk about more of these examples later as they come up. But say we look at that thermal energy system. The measurable property is the temperature. So you can measure the temperature of something. If that temperature changes, we measure how much temperature change that has. We calculate by subtracting the final minus the initial. And then we multiply by a constant. In this case, it's m for how much stuff you have, the mass, and c, which is a specific constant to just tell you the type of material. But that constant of how much stuff you have and this other constant multiplied by how much temperature change we have gives us an energy value. And that's, like I said, going to be different for each system. Once we get into calculations later in the week, this will kind of track more clearly. Our third energy interaction relationship is that the total energy of any physical system is the sum of the individual energy systems. And this just says if something has kinetic energy and gravitational potential energy and thermal energy, the total energy would be the sum of all those. So this is kind of a throwaway, hopefully pretty obvious statement. In a closed physical system, which just means that nothing is interacting with it, no energy is coming in or out, the energy change sums to 0. In other words, energy is conserved. And we write this as the change in energy total is equal to the change in energy system 1 plus the change in energy system 2 plus the change in energy system 3, etc. And that's equal to 0. So in other words, if a system is closed, no energy goes in or out. So if energy system goes up, maybe energy system 2 comes down, maybe energy system 3 comes down as well, but they all add up to equal to 0. So in other words, if something gains gravitational potential energy, it would have come from, say, its kinetic energy. This is just a way of saying if you've got all those bank accounts, money has to go between them. You can't take it from outside. In an open physical system, the energy change is equal to the energy gained or lost from the system. In other words, energy is still conserved. So this is energy total equals change in energy 1 plus change in energy 2 plus change in energy 3, etc. equals Q plus W. I'll explain what Q and W are in a minute, but for now just understand that this is the energy added or removed from that system. So in other words, if it's not closed, if energy can flow in and out of a system, we're just saying that however much energy changes in my system, that's going to equal whatever I threw away or whatever I pulled in. So even if energy is lost from a system, it's not lost from the universe, it just went to another system. And then lastly, all energy changes or transfers occur as heat or work. And this is just two ways that we talk about energy systems changing. Heat we refer to with the variable Q, work with W. We'll define these later as they become relevant, but I just want to kind of lay the groundwork here.